Hello, welcome to 22nd lecture in this Introduction to Proof series. We're going to be covering section 4.3 from JIAM today. It's about set operations, things like union and intersection and complements and all that. The layout today is, well, like I just said, we'll do union, intersection, and complementation. Talk a little bit about how we can tell when two sets are equal, and so develop some identities about sets. That will be dealt with in rather more detail in the very next lecture. So that's just kind of an intro to it. A couple of funky operations next that sort of are special to sets that don't have that not terribly parallel with anything in logic. And finally, I'm going to show you an application of set operations to 3D modeling, which I think will be kind of fun. So let's get rolling here. First, the definition. I want to say it very informally first. Given two sets, if you just take all the elements of both of them and glob them together until you get one big set, that's what it means to be the union. If, on the other hand, you look at only the elements that they have in common, just consider the things that are common between the two of them, that's the intersection. Very informal, imprecise, but it gets the point across, I think. The symbols for union and intersection are, the name of these are cup and cap, but the one is an upward opening rounded thing and the other is a downward opening rounded thing. They're just really meant to be rounded versions of the or and the and symbol. Okay. And actually that's not done haphazardly. The cup is actually the rounded version of the or symbol, and cap is the rounded version of the and symbol. And here's why. When you do union, which is the cup thing, that corresponds with or in logic. So union in sets is disjunction or in logic. And intersection corresponds with and. If you're doing the intersection of two sets, it's like doing the and of two logical statements. So let's do an example of that. Like usual, we'll work in a well-defined universe of discourse. This one, it's just the numbers from 0 to 10. We're going to define A to be the things in that universe that are prime. A is x and u such that x is prime. B is the things in that universe such that 3 divides into them. Okay, so, well, there's A, 2, 3, 5, 7. Right? Those are the primes that are less than 10. And there's B, 0. Oh, right, 0 is a number that's divisible by 3. 0 is divisible by anything. But also 3, 6, and 9 for proper reasons. Okay, so those are the two sets. What do the union and the intersection look like? Well, A union B, you kind of have to go back and forth between the sets and collect everybody. So we get 0 from B, then we get 2 from A, then we get 3 from B or from A, it doesn't matter. But there's only one copy of 3 in the final union. 5 and then 6 and 7 and then 9. Trying to indicate that you basically mesh the two lists together so that your union comes out in order. And by the way, if you're in a computer environment, you need to do that sort of thing. It's very nice if you know this is already sorted and you know that's already sorted. Then it's very easy to mesh them together and get a sorted list as your final answer. It takes less computation. All right, so there's a union. It's got 1, 2, 3, 4, 6, 7 things in it. Not quite as big as the whole universe. There's a few things missing, right? Let's see. What is missing from this? 1, 4, 5, 6, 7, 8, and 10 itself. So a couple of things missing, but it's a pretty big set. The intersection is just the singleton set with 3 in it. Does that make sense? What are the common things between 2, 3, 5, 7, and 0, 3, 6, 9? 3 is the only thing I see there. So a singleton for the result there. Okay, so notice that A union B consists of those elements of the universe that are either prime or a multiple of 3. See how the or connector works there? And similarly, A intersection B is the things in our universe that are prime and a multiple of 3. Now, what primes are there that are also multiples of 3? 3 itself, and that's it. That's why we get a singleton set for A intersect B. That might leave you with the feeling that intersections always come out to be singletons, and I want to dispel that notion because that's not at all true. There's certainly cases where you have multiple things in common between two sets, but just more practice of the same thing, spotting what the union and the intersection look like. All right, so same universal set, 0 through 10. I'm going to say A is the set of things that are perfect squares. A is x and u such that x is a perfect square, and B is the even numbers in our universe. B is x and u such that x is even. That's pretty good. A looks like this, 0, 1, 4, and 9. Everybody cool with that? And then B is 0, 2, 4, 6, 8, 10. B is a pretty big set, but there's plenty of odd numbers in this universe that aren't in B. So. Now when we take the union of these, both of them have a 0 in it, so we certainly get 0. A has a 1, so we get 1. B has a 2, so we get 2. Neither of them has a 3, so notice how 3 is not in here. Then 4 comes from A. Well, 4 comes from both of them. Why is 5? Oh, 5's not in either of them. Cool. 6, that comes from the B. 8 comes from the B. 9 comes from A. And finally 10 from B. So I think we got that right. That's the union. What's the intersection look like? That would be the things in common between the two of them. So we're looking for an even number that's one of these squares. 0 is 1, 4 is another. So yeah, 0, 4. But 1 and 9 they're not even, so they're not going to be in this intersection. So again, putting it in terms of the logical statements that these things are the truth sets for, A union B consists of those elements of the universe that are either a square or they're even, or both. Some of them are both. What is A intersect B? That's the things in the universe that are a square and even. So even squares. So let's be a little more formal with it now. Suppose that A is a set and it has a membership criterion P of X. I have previously used this subscript notation M sub A of X, but that gets a little cumbersome in this setting. So I'm just saying P of X is a open sentence. A is the set for which it's the membership criterion. Another way to say that, sort of in the reverse order, is that P of X's truth set is A. That's what we did 2 times ago, I think. So A is the set of all X in our universe such that P of X. That's how you define A. Similarly, suppose we got a set B and its membership criterion is Q of X, and so it's going to look like B is the elements of our universe where Q of X is true. Good. Okay, so the way we define intersection, I should have pointed this out before. I apologize. The symbol for union really looks like the letter U, doesn't it? The symbol for intersection looks like a letter N, a little bit anyway, like a lowercase n, but it's missing that little serif on the left side. And N is the second letter in intersection, so maybe the U is the one to remember. But I sometimes see those and go, oh, intersection. Anyway, yeah, A intersect B is defined via a conjunction, that is an and statement. So A intersect B is the X in our universe that make both P of X and Q of X true. The membership criterion for A is true, the membership criterion for B is true. Here's the similar definition for A union B. It's just really the same, except replace the symbol in the middle with a union. A disjunction symbol, the or symbol. It really, it's almost interchangeable with union. That's why it's funny that I made that mistake. Okay, so one final step. Remember what P of X is. It's literally the same thing as the statement X is in A. If P of X is true, then X is in A is true. And if X in A is true, then P of X is true. And likewise with falseness, they're logically equivalent sentences. So Q of X is also that sort of thing. It's X and B, but it's equivalent to the statement X is in B. And so you can re-express A intersect B in terms of these lines that look like X in something. X, A intersect B is the elements of our universe such that X is in A and X is in B. And the other one looks similar but with an or in the middle. The union is defined as the elements of our universe such that X is in A or X is in B. Cool. All right. Got to point out that because of the way we've defined union and intersection, they're defined in terms of conjunction and disjunction between, in terms of and or. And or had a whole pile of rules that they obeyed. There's all these really almost trivial proofs you can do that show that union and intersection obey those same rules. But in particular, I just want to say they're associative. If you have a bunch of things union together, you can put the parentheses in any way you want, and the answer will always be the same. So that means there's no ambiguity in doing the union of a whole pile of things all at once. You can have 19 sets union together, and it doesn't matter what order you take them in, so you can just say union of them all. And that leads to what I call the big versions of union and intersection. They're like sigma and pi notations for sums and products. Well, let's just see what one of them looks like. This is a union for an index that goes from 2 all the way to infinity of a bunch of intervals. All these intervals that look like they're closed intervals, square braces on both ends. The right side is always 1. The bottom side, or the left side, is 1 over n. So first, this is the interval from 1/2 to 1. Should I write that out? I bet I should. If you wanted to expand what that union is, it looks like the interval from 1/2 to 1, unioned with the next one would be the interval 1/3 to 1, and keep going because that one goes forever. The union of the interval with 1/4 to 1. Sorry, working on folded paper, so it's kind of flopping around on me. And then maybe if we've established enough of a pattern here that I can say dot, 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 you get the idea. That's an infinite line of unions tacked together. But this other notation is much more succinct, isn't it? So we should try to get handy with being able to look through one of those big union, or of course, intersection can also have a big version. Do it. All right, so yeah, that's the union of an infinite number of intervals. Here's a quiz for you. Can you guess whether 0 is in that union? Because you see the left sides of these are getting smaller and smaller and smaller, and there's infinitely many of them. Does it ever get down to the point where you throw up your hands and say, sure, put 0 in? I'll let you continue to think about that. Okay, so we've just seen set theoretic versions of disjunction and conjunction. There's one other operation we had when we were doing logic stuff. Well, there's multiples, but the next thing we dealt with when we were doing logic was not, or logical negation. Where does that come in this story? Whoops, I hit it twice. Suppose A is a set and its membership criterion P of X. What set has the membership criterion negation of P of X? That's really what we're asking. What in the sets will correspond to negating the P of X? All right, so let's try an example, and hopefully this will help us think it through. Again, the universe is 0 through 10, and this is a set we've seen before, the prime numbers that are in the range 0 to 10. So in this example, P of X is prime. That's what it takes to get an element. If that sentence is true, then that means you go into the set. And if that sentence is false, it means you don't go into the set. Well, then the negation of being prime is not being prime, right? X is not prime. That's easy. Maybe it's too easy because you want to. The other way you can always do a negation is say, it is not the case that, and then just spit out whatever the thing is. It is not the case that X is prime, but I think it's fairly clear to most people that translates as X is not prime. Okay. Well, what set is that? What things in our universe are not primes? It's all the things that are not in the original A we talked about. Not A was the set of primes between 0 and 10. Pick everything in 0 through 10 that's not in there, and that's called the complement. You've probably run into that before. Note the spelling. There's a different word that has an I right there, complement, and that means you're like saying nice things about people. Um, there's other meanings of that, but that's one of them. But complement means something that's complementary. It means it's together they make up the whole. There are two parts that make up a whole. So the way we denote that in the Giant book, and this is a pretty popular notation, is to put an overbar over the set. So a bar over the set means complement. I'll point out there are other fairly common notations, and people slip up. I may occasionally write the complement as a superscript C. That's another real popular way to denote it. Some people will put a prime that looks a little bit like you took a derivative, but if it's a set, there's no such idea as the derivative of a set. Well, anyway, yeah. So sometimes you'll see complements denoted other ways, but I think the bar is probably the most common. So what is the formal definition? Given a fixed universal set U and a set A contained in U with, now I'm going back to the old subscript notation for its membership criterion, M sub A of X. A bar, A's complement, is the set of X in our universe such that not M sub A of X. Here's another way to say it. A bar is the things in our universe such that X is not in A. They got to be in your universe, but you're not in A. Without this first part of saying X has got to be in the universe, you would have a very funny situation when you started to deal with complements. And there's a kind of a big long spiel about that in the Giant book. Just let me point out that there's an awful lot of stuff that's not in our little set of what was it, 2, 3, 5, and 7 that was the set A. There's plenty of things in there that aren't even numbers. So if you're not 2, 3, 5, or 7, you could be the concept of harmony, or a musical note, or the hairs on my head. No, probably not that. We want things that actually exist. Anyway, the the question of whether this thing is well defined or not, whether we can really say what things are in it and what things aren't, is somewhat tied up with this idea of using a universal set that we've been doing. I don't want to get into too much detail about that just now. All right, so let's move on. We've talked about union, intersection, and complementation. Um, we'll use those operations to create some identities. And but before we can write an identity is something where you say one expression is equal to another expression. You kind of need to know what equals means. So let's see. Um, when are two sets equal? Well, let me preface this by saying we are definitely going to look at this in more detail. In particular, we're going to look at how we prove the two sets are equal, because that's kind of a big deal. It's often the case that um, you know interesting proofs we need to do are of the form show that one thing is really the same set as another. They may not look like they're the same set on the surface, but you prove something by doing that. So that's a standard technique, or actually a couple of standard techniques that we're going to need to learn. But for now, here's the idea. It's basically the same thing as if and only if is in logic. The idea of two sets being equal is that their membership criterion are equivalent. So, or the equivalence of statements. But that's maybe too much into this whole zen of showing you the connection between logic and set theory. What most people go do is say they have the same elements. Oh, well, wrong reveal. That's just saying what the thing before it said. Here's the one that says they have the same elements. It's just more direct, I think, to think about elements. If A is equal to B, then any element of A must be an element of B, and similarly, any element of B must also be an element of A. There's nothing in A that's not in B, and there's nothing in B that's not in A. That's the kind of idea. Another way to say it, they have identical lists of elements. If we sorted the elements in both sets and laid them next to each other, we'd see no differences. That's what it means to be equal. Contents are equal. But look at this phrase I just used. Any element of A must also be an element of B. That's what it means to be contained in, right? And the vice versa part is containment in the other direction. So a very nice way to think about equality of sets is that A is inside of B and B is inside of A. I shouldn't say it that way. A is inside or equal to B, and B is inside or equal to A, and those two things can't be true together unless A and B are equal. So you get this. A equal to B is equivalent to saying A is a subset or equal to B, and B is a subset or equal to A. So we're going to do some set identities next. There is a handout. I think rather than showing it virtually, I'm actually going to show it physically here. Let's see how well this works if I make the AirSots webcam view a little bigger. Hopefully that's close enough to being big enough for you to see. I hope you notice the layout is almost identical to the similar table that we had when we were dealing with logical equivalences. So, and the order of everything is the same. In that table, it's commutative laws, associative laws, distributive laws, De Morgan's laws. Most of the things that are written here just are the sharp, pointy symbols have been exchanged for the nice rounded ones. We previously had A and B is equal to B and A for the commutative law. It just turns into an intersection symbol for the commutative law of intersection. Distribution looks, oh, I'm sorry, I'm pointing at associative while I'm saying distribution. This is, everybody's got the same direction. Intersect and intersect equals intersect and intersect. So they're all, that's just an association moment. It's just been reparenthesized. First it was around B and C, now it's around A and B. And, you've got the same thing when there's a union version of it. Distributive laws here and here. De Morgan's laws look a little different because the way we did negation in logic was to put that hooked minus sign out front. But when we do negation in sets, it's the complement, and that's done with an overbar. But if you think about it a little bit, these are the same things. The thing on the left here, A, and I can actually point physically since we're here, that thing is the complement of the intersection, and this thing is the complements unioned together. So how do I say that again? The complement of the intersection, the union of the complements. The other version of De Morgan's law is the complement of the union is the intersection of the complements. Double complementation, double negation, same idea. If you complement the complement, you get back the original set. Now, some of these things are elements of set theory that we haven't talked about yet. We do have the empty set. So the idea that a set intersected with its complement is the empty set, does that make sense to you? Yeah, I think it does. What about unioning a set with its complement? You see, the complement and the set have nothing in common, and together they make up the entire universe. That's what these two set lines are saying. The set and its complement intersected give you the empty set. Unions, they give you everything, the whole universe you're in. The thing I haven't made explicit yet, but maybe you make this leap yourself by looking at this table, is what T and C, the tautology and the contradiction from logic, what do they correspond to in set theory? I'm not going to give that away because I want you to think about that. So, and plus we're going to have something in the activity for this set about that. All right, so I think that's enough of a whirlwind tour of the table of basic set identities. We don't need to say too much more about it. I'll just say, well, this is true too. It's a little bit redundant because everything that we just did is a mirror of something from logic. But in a few places, the layout is different, so it's kind of nice that we. Sorry, I've got to get this. Why can't I grab the corner of that? I'm going to put this thing back in its place. All right. Um, what else? The proofs of these results are really pretty tedious. They're doable, but they just all have, it's like a recipe book. You have a pattern that you have to do. It looks something like this. You have a set theoretic expression on the left side of one of those um, identities we're wishing to prove. You convert that into a logical expression. Then you apply one of the rules from chapter 2 from the logic chapter, and then convert the result back into set theoretic form. So it's just go over to logic, do something we already know how to do, then convert it back to set theory, and it turns, like for instance, commutation in logic it allows us to prove commutation in sets. We'll try a couple of those in the activity for today, but uh, it's not really worth doing too many of them because they are tedious, as I say. Oh, and we already did just examine the handout. I kind of took things out of order for this slide. Sorry. All right. So there's a couple of other operations that are not so much seen in logic. One of them has a relationship to something in logic. The other is different and unusual. Um, the first thing is called relative difference, also known as set minus. It's really the idea of subtracting the elements of one set from the contents of another. That's not a bad way to say it. Everything in A that's not in B. So uh, take away from A anything that it has in common with B. That's another way to sort of think about it. That's how we write it. It's a sort of a backslash A backslash B. That symbol, if you do LaTeX, that's actually written as slash set minus. So it's the standard thing. Many people do not use the set minus. They do use an ordinary minus sign, and that's perfectly understandable. But I'm kind of old school. I like the set minus. I feel like it's important to use the just right symbol for a thing rather than one that's sort of approximately right. Because subtraction really is a different thing, isn't it? I mean, subtraction is something that goes on between two numbers, not between sets. This is a different operation, really. It's taking away the elements of B from the elements of A. Okay, so here's the definition of that set minus. It's the intersection of A with B's complement. Actually, that's pretty much what this first sentence says, isn't it? Everything in A that's not in B. So you want to take A, and things that are not in B would be intersected with that. Okay, so that's not a commutative operation, I'll point out. A minus B is not the same as B minus A. Good. But here's the cool thing. This is the other oddball operator. You can build something that is kind of a symmetric, a commutative way to do subtraction. Well, it's not really subtraction, but it's called a difference. In fact, it's known as the symmetric difference. So we can create a commutative operation by forming the union of the relative differences in both orders. It looks like that. Now, the symbol for the symmetric difference is just a triangle, a triangle B, and what you do is form A set minus B and B set minus A and union them, hook them together. That's known as the symmetric difference. I said that already. Oh, it was because it was in the title of the slide too. Now there's an exercise on page 183 in GIAM about the symmetric difference, and it's a great chance for us to practice doing a two-column proof. So I think it's worth our while to run through it. Let me first pull up the exercise. It's right here, and the GIAM has a lot of these exercises that are mid-text. As you're reading along, it says exercise, and you're supposed to do them. So I don't know. I got the sense the first couple of times I was using this book with a class that the students weren't really doing those exercises, and so I put this whole riff in here about like hey man, you read right past that exercise without even pausing. But that mostly was a chance to do something I thought was a little bit fun. So this is kind of a puzzle. I'd like to show that A symmetric difference B is equal to this: A union B set minus A intersecting B. But of course, a symmetric difference B is defined like that. It's the union of the set minuses in the two different orders. So can we convert this one into this one in a nice step-by-step fashion? In other words, write a two-column proof. Now, if you go to the next page, this is what they provide you with, or I provided you with. It's a list of all the steps in the proof, and together with their associated justifications, but it's all in the wrong order. Right? So I have that here, and I pre-prepared it so that we can tear it up. And the first thing I'm going to do in terms of tearing it up is notice that I definitely know what the first step is, because the justification for it is it was the given thing. So I'm going to just pull that one off. That's going to go at the top of the page for sure. I did bring out some Scotch tape. I'm going to see if I can just tape these down a little at a time as I go. Ugly, but and it's at a weird angle now. So what comes next? Now the things are over here in a bigger form, but can you see what would come next? Gee, it seems to be working the wrong direction. I would have started with the definition of the relative difference. But I started in this case. I said the thing that was given was the right-hand side of the inequality. Maybe that makes sense because it's the more complicated thing, and you'd like to be able to go from complicated to simple. Where are we supposed to end if that's where we start? If the place we start is the right-hand side, let me jump back to the statement. We're starting with this. Well, we want to end, in that case, with this. So that gets me something. I know, where is that statement in here? It's right here. It's one of the ones near the bottom. So let me pull that one out, and we'll tape that to the table right down there at the bottom. I'm not sure if it's all going to fit, but let's see. Okay. So how can we get these things together? Well, the symmetric difference, it says we use the definition of the symmetric difference. Let's see if amongst these things we notice where something is that looks like the definition of the symmetric difference. It's weird because it has a label on it that says it's something about the definition of the relative difference, but remember that it was the thing before it. So we're looking for that one, the one that says, I just found it. That should be the step that comes right before that final step. I'm going to take it down. So far, so good. What comes? Let's see if we can work downward from the given statement this time. That slantiness is really getting to my brain, so I'm trying to fix it. Probably by making it worse, but here goes. Yay. Okay, so where could we proceed from that? That is a relative difference, isn't it? It's the union minus the intersection of the things. So is one of these, let's look at on this version, is one of these look like the definition of the relative difference of, well, in fact, wow, it's going to say definition of relative difference, isn't it, somewhere? There it is. It should be the first one intersected with the complement of the second one. Yeah, so it was right next to the thing that it's supposed to follow. This one. It's actually sitting there right in front of me. Okay, where's the tape? we're almost there, right? There's just a little gap in the middle. Now, I think sadly the gap is going to be too small to fit all these in because there's still 5 steps, and I think there's only room for about 4 of them. Because I'm kind of being a moron right now. There's plenty of room on this screen. I just need to move it down. Okay, so let me do that. I had a girlfriend once that called me the dumbest smart guy she ever met, and there was a great example of it. Is that going to be enough space to get our remaining 5 steps in? If not, we'll adjust and move that down. Looks like it'll just, yeah, it's going to be short. That should definitely be good. Give us space to get these things in here. So, do you realize this is a little bit of a case of the forward-backward method we're doing here? Which would you rather do next? Work from the top or try to work backwards from the bottom? There's only so many possibilities. I've got a line on here. One of the lines says De Morgan's law is the justification, and there's a complement of an intersection there. Does this De Morgan's law come from that? Not looking good, is it? Huh. What? Let me try them in order then. It's not De Morgan's law there. Could it be that we did this thing next? Distributive law from there? Wow, I don't see how that's at all related to it. So no, not that. The identity law somehow? Not seeing how that's related to that thing at all. Okay. Wow, complementarity. Comes up sometimes. That doesn't look like it's related. Could it be this last one? Oh, yeah, it is. They always say you always find a thing the last place you look for it. Do you see how that's what happened in this? We distributed the complement of A intersect B across the other piece. We took the intersect sign together with this whole chunk, the complement of A intersect B, and we distributed it into the other set of parentheses. Okay, so that's cool. I'm going to tape that down. I keep setting the tape down somewhere funny. Excuse me. All right. Now that is interesting because there was one of these ones we saw a little while ago that looked like a crazy distribution, but oh no, that's not going to be it. Maybe the De Morgan? Yeah, look at that. That's what did they do there? They did De Morgan twice for both the things that look like the complement of A intersect B. Yeah. So that's one step away from the thing above it. That must be what comes next. It's funny that this becomes a pretty easy puzzle when the pieces are given to you. When all you know is the first part and the last part, then it's a little more challenging. But like this, it's pretty doable, isn't it? All right. I think probably we've got another distribution going on here. And that's where we get to our sort of maximum complexity. This is a nice example of one that gets uglier and uglier and uglier, and then simpler and simpler and simpler until we get down to just A triangle B. Do you think that, am I correct that this is the right result? There's actually 2 applications of the distributive law in here. We're distributing B across A complement union B complement, B in the intersect. We're also distributing A and the intersect across this other union. That's what we get. A intersect A complement, union A intersect B complement. But you can probably see it fine. Then complementarity. If you intersect a set with itself, you get the empty set. And what the last step is, the empty set acts as an identity for union. If you're unioning means glob all the elements together, they're the 2 sets. Well, if one of them's empty, it doesn't contribute very much. So the result of the union is just whatever was in the other set. All right, so that's actually a valid proof, isn't it? The final step would be the connection from here to here. We didn't talk about that, but that's just the definition of the relative difference. Kind of used in the reverse of what we normally think of it, but that's fine. A intersected with B's complement is A minus B. All right, so that was fun. I was sweating a little bit whether I was going to get it done right, but in the end, we got there. So good. Let's uh, let's pop back to the slides here. We got through that exercise. Oh, the 3D solid modeling. This is what I'm really looking forward to showing you guys. Um, this is a program that I absolutely love. It's called OpenSCAD. I'll show you a different model first. Um, the reason I love it so much is it's literally seems like somebody designed a interface for doing 3D modeling that was designed for computer geeks and mathematicians. And most of the interfaces for doing 3D modeling were designed for artists, which well, I kind of think of myself as an artist, but the rest of the universe says no. Um, anyway, this is just I created a module that creates an icosahedron. You can move it around, see it from different angles. This is just a sample. Um, if you, I think we talked about this solid once before, but it's familiar to people who play like Dungeons and Dragons and games like that because it's got 20 sides on it, so it's appropriate for a 20-sided die. Number outcomes from 1 to 20. But the other thing I did here, I wanted to show you. Let's comment on something. I wanted to show you a couple of basic objects. So the first one I made a kind of a 3D version of a plus sign. Now that is actually defined in this module here, but I don't want to focus on how you do it more advanced programming. I just want to show you something simple. So we'll have this plus sign that I created elsewhere. And its geometry is fairly obvious what it looks like. Um, it's a 3D plus sign, right? Actually, there's a shape that there's an object that has this shape that people use in the real world. It's called a jack. If you ever played the game of jacks, and in the military, a thing like this is known as a caltrop. It goes back at least to the Phoenicians, possibly before that. It's you make one of these things and have pointy things on the ends of it, and then the other guy's soldiers step on them and it hurts their feet or their horses. They even make giant size ones of these things that are suitable for slowing down or stopping tanks. So yeah, giant plus sign. Anyway, the other object I have, let me switch what thing was commented. Reveal the sphere. Now, this program has the ability to create all sorts of primitive geometric objects, like a sphere or a cuboid shape. Um, there's I don't know, 7 or 8 different things: cones, cylinders, spheres, more. You can type letters and have it make like an extruded version of a letter. Um, I just for now want to stick with our plus sign and our sphere because I want to show you that the way this solid modeling program works is just exactly the math we just were learning about. It's union and intersection and difference and things like that. So if I put the two of them uncommented, we get a plus sign poking through the faces of a sphere or the outside of a sphere. Um, this is really the same thing as if you took the union of them. Oh, whoops, gotta learn to spell. ION. Got an extra O in there. Union. There we go. So union is an operation, and as such, the way this language works, the things that come after a set of curly braces are the arguments to it. So what it's going to do is form the union of my plus. By convention, people indent these things, and it's not going to look any different from what we had here. It's just it's sort of now treating them as a single thing. Let's see what the intersection looks like. What will it look like if I intersect? Okay, run the update. Oh, now what have we created there? It's like a stubby plus sign with rounded outsides. Well, it's the part of the sphere that was also inside the plus sign, or vice versa. It's the part of the plus sign that was also inside the sphere. So that's what it looks like if you intersect. What if you took the difference of things? Just change that word into difference. Huh. That's the starting with the plus sign and remove the sphere from it, and it falls apart. It's got all these 6 disjoint chunks to it. How about if we switch the order? I should be able to copy and paste that. Yeah. I don't know if that's going to make a difference, but I want it to look nice. So there we go. The difference of the sphere, and take away the plus sign. That's kind of like I thought it would look like. This sort of software I'm doing is not just for making images that you move around on the screen. There's a way to output to what's known as a STL file. And you feed an STL file to a 3D printer, and it'll make you a thing like this, which is kind of cool because if you had to make a thing like this with regular machine tools, you couldn't. It would be really hard. It's very hard to make a square hole in something. There is a way. There's an old school way, and then there's a more new school way, but it's not an easy thing to do. Whereas doing it in the virtual land here on a computer is trivial, and a 3D printer just makes whatever you tell it to make. So the downside is 3D printer output objects are sometimes not as sturdy as you might like. Okay, so I guess have I shown you all that I wanted to do in terms of making models with OpenSCAD? I believe so. The other things in this 3D modeling setup I wanted to show you are, one, I just want to show off a little bit, frankly. I have an account at the MakerBot's website, which is known as the Thingiverse. A lot of people post their designs up to the Thingiverse, and you can find all kinds of interesting things to play with there. Download them and make them yourself. So this is my personal list of designs. One of my favorites is this thing. It's actually one of the things that people have liked a lot. It's a magic decoder ring, basically. If you've ever run into one of those, it has 2 alphabets going around a ring, and those are free to slide or to rotate around one another. So you can set up a secret code using it that you would substitute one letter from the alphabet for another. Another thing that I needed when COVID first struck and we had to shut down and go online was a device for holding my cell phone in a tripod. So this is a tripod adapter that uses some rubber bands to basically grip the cell phone. That one's actually not a real. This is a cool thing called Steiner's Roman surface. This is another one that's a favorite of mine. It's called the Costa surface. Jose, I forget his middle name, but Costa is his last name. Discovered this new example of what's known as a minimal surface in the 70s or 80s, I think. I have other things like models that are intended for teaching things in like Calc 3, what contour lines look like on a surface. Well, I'll show you some other ones. These are physical. This is a physical model of a Riemann sum of a surface. It turns out to be the surface there was rather coarsely subdivided, you can see, but here's the same thing with a more fine subdivision. Doesn't show up very well because it's black and the light's not that good. Anyway, that's finally this is the smooth thing. It's an object or a surface known as the monkey saddle, which is it's like a regular saddle, except if you have a tail, it's really nice to have the monkey saddle because it's got a place for your legs and your tails where it goes down. Anyway, there's lots of fun stuff that you can do with 3D printing. This is another variant of the Costa surface that I had printed, which I was going to send that to an art exhibit, but COVID again. Anyway, I have to say that my attempts at using 3D printing to visualize things in mathematics are somewhat amateurish. The other thing you can do is just search for math on the Thingiverse, and you'll see there's a huge community of people that are creating all kinds of weird and fun toys to play with that are mathematical. That's a thing known as the Seifert surface of a knot. I don't know why that math bowl is of interest, but tons and tons of things. Yeah. But the guy who is truly a pro at using 3D printing to do mathematical stuff, and I have to say I'm kind of a fanboy of this man. Has my great respect. Henry Segerman. I actually have his book right here, which I highly recommend. It's called Visualizing Mathematics with 3D Printing. What he's visualizing on the cover of that is a thing called the um, stereographic projection from a sphere onto the plane, basically using a little laser, well, not a laser, sorry, an LED light source, taking a really weird looking curved surface drawing basically of a strange shape on a sphere and projecting it, and it ends up looking like a perfectly flat, nice grid projected on the plane. So Henry Segerman has a fantastic YouTube channel, which I very much recommend going and perusing. There's a lot of fun stuff to be done there. And I think that's enough for 3D printing. Was there anything else in our slides today? No, come to an end. Well, that was a good auspicious place to end with one of my favorite mathematicians. So next time we'll be doing 4.4. You should definitely read that a little bit in advance, and have a great rest of your day.